Today we're going to integrate 1 plus ln x over square root minus x ln x times ln minus ln x between 0 and 1. First course of action, we're going to say u equals minus ln x, so du equals minus 1 over x dx. Our bounds are going to be infinity and 0. We can use our minus sign to flip them back to 0 and infinity from the derivative. That x is e to the minus u. So now what we have left to do is put in the u instead of x for my original integral. So we have 1 minus u over square root u e to the minus u multiplied by ln of u du. And rewriting this, so we have just 1 e to the minus u term. We get e to the minus a half u times 1 minus u times the natural log of u over square root u du. So we're going to get rid of that square root u term by doing substitution for it. So you do v equals square root u, dv equals 1 over 2 square root u du. So now we just have the same bounds as before, but 2 out the front. And now we have e to the minus a half v squared times 1 minus v squared times the natural log of v squared dv. Okay, so we're going to split this integral up into 2 integrals. We're going to have 2 lots of integral between 0 and infinity, e to the minus a half v squared times ln v squared dv. And then we have minus 2 lots of the integral of e to the minus a half v squared. And this one's multiplied by v squared ln v squared dv. So we're going to focus on this integral on the left here for now. We're going to do integration by parts. So we're going to differentiate e to the minus a half v squared, which gives us minus v e to the minus a half v squared. And then we're going to integrate the natural log of v squared, which gives us v ln v squared minus 2v. And you can do that by taking out this exponent using that log law. So, putting this together, we have 2 lots of, and then we're evaluating e to the minus a half v squared, v ln v squared minus 2v at 0 and infinity. And this just becomes 0. So what we have left to actually worry about is plus 2 integral between 0 and infinity, and then we have v squared e to the minus a half v squared ln v squared minus 2 v squared e to the minus a half v squared dv. What you might notice is that if we were to continue writing our that should be a minus. If we were to continue writing our problem with our second part of the integral, which we weren't focusing on just now, we would have e to the minus a half v squared ln v squared dv. And you'll see that this just cancels out with this term here. So it's just this middle integral we have left to evaluate, which is nice and easy. So let's get started. So we're just going to integrate minus 4 lots of integral between 0 and infinity of v squared e to the minus a half v squared dv. And I'm just going to write that in terms of x, because that does not matter. E to the minus a half x squared dx. So we're going to do some integration by parts. We're going to say what we're differentiating is x. So du equals 1. Then we're going to integrate x e to the minus a half x squared, which leaves us with minus e to the minus a half x squared. Putting this in together, we have minus 4 minus x e to the minus a half x squared between 0 and infinity, which again is 0. And then we're just going to do minus 4 integral between 0 and infinity of e to the minus a half x squared, which we know as the Gaussian integral. So you can say that this is minus 4 over 2 lots of square root 2 pi, which just leaves our final answer as minus 2 square root 2 pi. There you go.